Okay, let us start. Mm, I'm sharing the screen. Okay, is this visible?
Yes, sir.
Okay, okay. So let me start with last question I left in last class. That's what is the significance of entropy? So first question is so as we know basically that entropy is defined like ds is actually related to our heat change d cross q divided by t, or let's say small cross q divided by t. This is the definition of entropy as we have studied. Means let's say we are if we considering a system, any system, and this system is exchanging heat d cross q amount of it with the surroundings at a constant temperature T, then we can say that the change of entropy is will be defined as d cross q divided by T. But there are some mm, in between things are there, just like this total definition is correct as per we are considering the reversible process. Okay, so let us first discuss what does it mean, the reversible and irreversible process. Then we will understand significance of entropy. Okay, let's say a state is evolving from A to B. It can evolve in various processes. Let's say this is path A, path small a, small b, and so other. There may be many other paths as well. But while evolving, the state function, if we are considering any state function, that will not depend on path. We know these things. State function is totally path independent. That will depend on state A and state B. So let's say x is a state function, then we can say that del x will be xb minus xa, and that will same for any path. That maybe go through path A, or that maybe go through path B. For any path, it will be same. So if you considering any state function, this is true for any state function. Now we are considering now that a path is a reversible path. This is a, let's say this is a reversible path, and path B is actually a irreversible path. What does it mean? That this state A is a equilibrium state and state B are also equilibrium state. We are considering the changing of state A to state B. That means from one equilibrium state to another equilibrium state, and that change can be occur through two different types of path, reversible or irreversible. For understanding better understanding, we are considering, let's say state A is this state. Some amount of gas is there. It has a particular P1, V1, P1. This is state A, and now it's changing to another state. Same gas, but P2, V2, T2. So it's changing its state. This change can be done in both ways that we have to understand. What does mean reversible and irreversible? So for better understanding, we are defining state like, let's say pressure is fixed. Here pressure was let P, volume V1, temperature T. Here also pressure and temperature same, but volume changes. Volume changes from V1 to V2. So this change, if we understand very easily, trivially, then we can think like that. This change V1 to V2 can done in very in small steps. Means let's say first we are changing from, this is V1, then small change is there, then again small change, small. In this way we can changes up to V2. Let's say this is the V2. So V1 to V2. This change is called the reversible change. That means system is not understanding that the state of the system is changing. We are changing the state of the system, but system is not feel that. System is not able to feel that. System is is thinking that he is on a equilibrium state. That means state A. But we are changing that A to first A plus dA. We are again we change this way. We are changing in small amount, and at for infinite number of changes, we arrived on state B. This type of procedure is called reversible process. But we can do it directly, just go from V1 to V2. Then that will call irreversible process. There are two types of process. This is the in basic definition. Probably we are all aware of this definition, but still it's important to define entropy. Why I am saying this? Because the reversible process is basically does not exist when we are in a practical life, day-to-day life. There is no reversible process. We are basically dealing with irreversible process. So we can think like that. Irreversible process is a real process, and reversible process can thought as an ideal process. So, but in thermodynamics, most of the laws, most of the equations are basically derived considering the reversible process because it's easy to derive. But for irreversible process, we can't do that easily. But here, the entropy is very important because it actually says that whether that change, that process will be spontaneous or not. Okay, entropy is actually guides a process. Any process will be spontaneous or not. What does it mean? First law of thermodynamics does not say that. We we can't have any idea from the first law of thermodynamics whether a process, any process, that may be a chemical process, that may be any physical process, any process, whether that will be allowed or not. That means that will occur in spontaneous way or not. We have to understand that spontaneous process means we have the definition of spontaneous process is if you make a ignition, if you initiate the process, then that will occur by its own. That is the definition of a spontaneous process. Means let's say if you um, if you light a candle, then the candle will burn totally. But for that, first you have to light the candle. That means we have to initiate initiate the process. If you initiate the process, then it will go by its own. Okay, that is called the spontaneous process. But and non-spontaneous processes, that will not be that will not completed by its own. For that we need to push from outside, or that will I will come into later. But that is the definition of spontaneous and non-spontaneous process. Basically, these irreversible process are actually spontaneous process. Irreversible processes are spontaneous process because if you initiate, it will be completed by its own. So it's a spontaneous process. But reversible process are not like that. Reversible process means that we are changing a system very infinite small way. So from A to B, if you think like that, then it is a reversible process. For that, it will not occur by its own. It's not a spontaneous process. So you have to understand that in that way. Okay, so now how does entropy came into picture here? Okay, so now this equation del S, the change of entropy, is basically equals to this B cross Q reversible by T, not B cross Q irreversible. That means, as we know that Q dq is actually path function. ds is not path function. ds is a s is a state function. So ds should be same for both process. But That means we can write ds reversible is equals to ds irreversible. That is okay. From A to B, we are considering this change from A to B. For that, ds reversible should be equals to ds irreversible. It will be same for any path. It's path independent. But d cross q reversible, that should not be equals to d cross q irreversible, because heat change, the d cross q is basically path dependent. That is a path function. So d cross q reversible is not equals to d cross q irreversible. So we can write ds, and ds reversible and irreversible both are same. So you can write like this. But so here we can write it is not okay. Now d cross q reversible is not equals to d cross q irreversible, as I have written here. So we can also write this. This is, we know, this is ds reversible. This thing is not ds irreversible, because ds entropy change is same for both processes. It may be reversible, may be irreversible, but entropy change is same. So it does not equals to d cross q irreversible by d. So we can write that. Basically what happens, this d cross q irreversible is actually less. So we can write that ds reversible, or ds, it may be anything, equals to d cross q reversible by t, plus we have to add something. Let's say 5. Actually this is less than, ds is greater than, d cross q by t is less than. So ds reversible is greater than d cross q by t, so we have to add something. This part we have to add, then only it will be equal. This part is called the entropy production. This is called the entropy production. Okay. So now we know that if for any process, if del S overall entropy change is greater than 0, then that process will be spontaneous process. As I mentioned earlier, the entropy will define whether the process will be spontaneous or not. If del is universal or total, that is already discussed in class. If it is greater than 0, then that means that the process is a spontaneous process. It essentially means that, I'm not going to derivation detail, that if phi is greater than 0, then the process is actually spontaneous process. That means if entropy is produced, or irreversible process here, then that process will be a irreversible process. That phi should be greater than 0, that entropy production. Okay. And at equilibrium, the phi should be 0, because then it will, this greater than will be equal, and phi will be 0. Okay. So this is the basic significance of entropy. That's entropy is basically dictating whether a particular process will be spontaneous or not. We can think like in that way also, but basically this is the main statement, which is actually the Clausius inequality. The Clausius inequality basically define that the process will be spontaneously or not. So that is the importance of second law. The second law and the entropy, we can think these are the isomorphic things, same things. The entropy actually differs. That's why the entropy is very important. Later, we will see that in free energy is also important. Actually, uh, this is our one and only guiding factor to be a spontaneous process. If it is greater than 0, del S universe, that means del S universe is del S system plus del S surroundings. Yes. Hello. Yes. Is there any question?
No, sir. Somebody has joined.
Okay, can you mute yourself? Otherwise, I have to mute. Okay, um, let's connect. Okay, so Taylor system plus Taylor surroundings. That this is the main guiding factor. Later we'll see that we can also think in terms of free energy.
Sir, I have some doubt
Yes,
on
yes,
regarding entropy.
yes.
In the definition of entropy,
Hmm.
there is always a term temperature.
Yes.
What does this temperature mean? It is average temperature or it is constant temperature?
No, no.
How does
For that process, when we are defining entropy, let's say a thing, a system, any system, and it's a system, and rest of the part is the surroundings. So now we have to think that that system is in equilibrium. Okay, we are talking about, let's say,
oh
state A or state B. That means the thermal equilibrium is there. That means temperature is not changing. Then only we can define the entropy. That T is the fixed T.
okay sir.
Okay,
Okay sir. Thank you.
okay. So now let us move to our question answer part. First question, inform it second actually. So let me write it first, then we'll discuss. If there are any other question regarding theory or the videos uploaded in YouTube, then you can also ask me. But you can stop me and you can ask me. For reversible change of ideal gas, we have to prove these two equations: CPln P2 by T1 minus NR ln P2 by P1. This one is the first. These equations are very important because there are various numerical problems can be formulated using these relations. These two, these two equations. Okay, so let us start. We have to keep in mind that for ideal gas and for reversible change, these two are important factors. So we know that du is equal to CVDT for ideal gas. Last class we have discussed this because there was another term like this term is there, I think. No, this term. Yes, this term is zero. Let me write it explicitly. Total form is this. Okay, but for ideal gas, this is zero. If it is constant temperature, then du will be zero, so this term will vanish and only CVDT remains. Okay, so du equals to CVDT for ideal gas only. Okay, so now what we can write, um, du, if you use the first law says that du equals to TdS minus PdV. You can derive that. Let me derive it. D cross Q plus D cross W, and D cross Q is TdS and this is minus PdV. So it is TdS minus PdV is CV dt. So ds should be CV dt by t plus P dV by T. Now, as this is a ideal gas, so we can write it. Ideal gas PV equals to nRT. So P by T can be written as nR by V. Now we can integrate. So it will be, let's say, S1 to S2, T1 to T2, and V1 to V2. Then it will be del S. It will be CV ln T2 by T1, and this will be nR ln V2 by V1. This derivation we know. This was done in class already. But here we have to prove in terms of CP, not in terms of CV. So we have to do that. How can we do? It's easy. Now we know for ideal gas, Cp minus Cv is basically nR. Hence, we can write Cp is Cp minus nR. So if you put it here, then you have that del S will be Cp minus nR ln T2 by T1 plus nR ln V2 by V1. Okay. So first term will be Cp ln T2 by T1. This is okay. But the second term will be nR ln V2 by V1 minus ln T2 by V1. Okay. So we can write it. It's okay. Yes. So it will be nR ln. So we can think like that. V2 by V1. Okay. Let us make it plus. If it is plus, then it will be T1 by T2. Okay. So if it is T1 by T2, then it will be V2 T1 divided by V1 T2. And for ideal gas, we know PV equals to nRT. So if it is PV equal to nRT, then V by T will be V by, here we can write V by T will be nR by T. So we can put it here. It will be Cp ln T2 by T1 plus nR ln. This is V1 by T1 here. So V1 by T1 and V2 by T2, we can think like this. This term can be things like that V2 by T2 into V1 by T1. Sorry, T1 by V1 in this way. So now V2 by T2, what will be V2 by T2? V by T is nR by P. So V2 by T2 will be nR by P2, and this will be nR by P1. nR will be cancelled out. We can write it that del is V2 by P1. This is another form. Okay. Now we have to prove the third one. This one already done. Now we have to prove the third one. Here both are there, CV and CP. So one thing we have to understand that this, when we use this relation, there are three relations basically. This is one, this is two, and another one we'll have, then we'll have three equations basically. Here we can see that temperature and volume is changing, right? E is changing and V is changing. So when for a question or for a process, when we will see that temperature and volume is changing, then we'll use this equation. If we see that pressure or temperature is changing, then we have to use this equation. Or if you see that pressure and volume is changing at constant temperature, then we have to use this equation. Okay, so we have to keep in mind all of three, or we can derive from one to other, but it's better to remember. Um, okay, now for the third one. So we can do it from here as well. Okay, okay, let me do. Okay, now let me start with previous equation, this. Okay, so you can write it. See, okay, because PV equals to nRT, so P1 V1 equal to nRT1, and also P2 V2 equals to nRT2. So nR will be cancelled out. So T2 by T1 will be P2 V2 divided by P1 V1. And here we can write nR ln, okay, V2 by V1. So it can be written as CV ln V2 by V1 plus CV ln V2 by V1 plus nR ln V2 by V1. If you decouple these things, then it will be CV ln V2 by V1 plus CV plus nR ln V2 by V1, and CV plus nR is basically CP. Okay. So there are these three equations are important. Equation number 3. Okay. So now we are moving to the third question. This is very important question. What are the conditions for the spontaneous process in terms of internal energy, enthalpy, this free energy, Helmholtz free energy? Okay. This we have to understand. What does it mean? So what we have seen that del S universe.
Excuse me, sir.
Hmm.
We have left out with one query of previous lecture.
Hmm.
Why always CP always greater than CV?
Okay. That is also a okay. Okay. Yes. Can you explain why CP is always greater than CV? For ideal gas, we know. For ideal gas, it
CP
is N.
CP there is scope of volume expansion. Due to volume expansion, some input of heat is there to allow
Hmm.
expansion, so that CP greater than
Yes.
CV.
Yes.
In
Yes.
CP,
Yes.
CV there is no scope of volume expansion, so
Hmm.
pressure volume work is not there.
Yes. Exactly. So if you look at the definition, the CP is D cross Q divided by del T at constant pressure, and CV is same but at constant volume. So let's say this is our initial state. Okay, so now we have to expand. This state has temperature, any temperature T. Now we have to increase the temperature by 1 degree at constant volume. But that means we have fixed the volume. If it is V, then volume will be V. Volume will not change, but we have to increase the temperature. So we have to give heat d cross q amount of heat we have to given, let's say. So then the temperature will be T plus 1. And that heat is essentially the CV, the amount of heat required to increase the temperature by 1 degree. That is the definition of CV, because it is a constant volume process. So now, if you see that the volume is here, actually the volume is fixed. So if volume is fixed, then there is no mechanical work because the piston is not expanding. If there is no mechanical work, then d cross W is totally zero. Now, if d cross W is zero, so essentially du and d cross q are same. Means that you are
Yes.
giving, if you are giving the heat, it will change the internal energy du. And we, as we argued before, that du essentially the signifies the temperature. So temperature will increase. But for a constant pressure process, what happens? We have to fix the pressure. Let's say here pressure is P and temperature is T. Now again you have to increase the temperature by 1 degree, but keeping the pressure fixed. So that means the gas will expand to that pressure constant. The gas will expand. So now the temperature goes P plus 1. You give the heat d cross q, but the volume increases, because what happens when you give the d cross amount of heat, that uh, in temperature internal energy is increasing, the temperature is increasing, that means the molecules are now moving faster, the kinetic energy is increasing, and that will give more pressure here. That's why the gas expands, and when the volume again expands, then eventually the according to Boyle's law, the pressure will decreases, and eventually it equals to P, and then the pressure will remain same. That is the Boyle's law. So it will go to T plus 1. Here, what happens as so del V is there, it is not equals to 0. That means D cross Q is not equals to 0. There is a non-mechanical, sorry, there is a mechanical work. So if there is mechanical work, then D cross Q is like this. So we can write it like D cross Q should be here du plus PdV. But we have to increase temperature by 1 degree. Means you are giving the heat. That heat is utilized in two ways. It is increasing its internal energy, as well as it is doing the mechanical work. So to have the increment in temperature by 1 degree, we have to give the more amount of heat compared to a constant volume process, because some amount of heat is utilized to make this mechanical work. So that's why always CV will be less than the CP. Okay.
Okay.
Okay. Mm. Yes. So in this question, the del S, as we discussed earlier, the del S universe always be greater than zero. That is the definition of.
Hello, hello. Shall I ask you one single question, sir?
Yes. Yes.
Sir, in the assignment one, the second problem that is given is, I think it is wrongly given. I think the options are wrong. I think.
Okay. But assignment one deadline was, as I saw, that was 7 February.
Yes, I agree. But the problem in the second problem that is given in the assignment is not matching the options. The answer is not matching with the options.
Okay. Okay.
Can you
I will
please
do
go
it.
through? Can you please go through that?
Yes, I will go, because as the deadline is 7, that's why I thought that I will discuss in the next meeting, in 13th.
That is okay, but the question itself is given. The question is okay, but the options are not correct. I think.
Okay. Okay. I will see.
Just no.
If it
Just
is.
please go through it, and if you feel that the options are wrong, then just correct the options. That's it. I'm not asking you to solve the question. Yeah, I'm just asking you to correct the options.
No, I don't have that authority to correct that option basically.
Or you
Uh,
just or you just suggest if you feel no, if you feel in
I
that way, just
can
to solve.
I can inform that instructor. Otherwise,
Okay.
I can solve the question and providing the right answer. That I
That's
can.
okay. Next class session, providing answer is that's okay. That's not a big problem. My question
I
is just
understand.
if you yes,
Okay,
just
okay.
forward the same to the other person who is taking this charge, is
Mm,
looking after this, and then you just if possible try to change the options if you feel it is wrong.
okay, I will go through the question, and if it is wrong, then I will obviously
Thank you,
inform the
thank you.
instructor.
Please proceed. Thank you.
Okay. Okay, so this was the condition for spontaneous process. But here it is asked that we have, yes, yes. Okay, so now we have to identify the conditions for spontaneous process in terms of internal energy, enthalpy, Gibbs free energy, and Helmholtz free energy. We know in terms of entropy, but here we have to derive for other processes as well, other parameters as well. So how we can do that? Okay, so actually we can write it in ds form as well, not del s or ds. These are the same thing. We know that du. What is the definition of du? We discussed here. Yes, TDS minus PdV. So TDS minus PdV. So we can write del U, or okay, let's say du del V at constant. S is actually temperature. Okay, this is okay. But okay, let's say for constant volume, what we can write, du is equal to TDS. Okay, for constant volume it is. Now here we know that the del S or ds, anything that should be greater than 0. If that is greater than 0, then it is a spontaneous process. So from here also we can see like this. mm, if it is not a constant volume process, then in general we can write that ds is actually du plus pdv. Okay, so if tds is equals to du plus pdv, okay, then for can write it that du S and V should be less equals to 0, because ds up is greater than 0. If it is, then it should be this condition. Okay, then only it will be a spontaneous process. If it is, then essentially we can also derive the other cases, the uh, enthalpy, Gibbs free energy, these things we can also derive. First, okay, the next is our enthalpy. For enthalpy it is Bh Sp less equals to 0. If it is equals to here, if it is equals to, that means that is a reversible process, because reversible process ds is 0 for equilibrium, not equilibrium process ds is 0. For spontaneous process ds is greater than 0. So equality means that that is a equilibrium, but greater or less than sign essentially means the continuous or irreversibility. Okay, this is enthalpy, and other one is Gibbs free energy. How we can understand this? In if you look at in, let's say you have to remember these things, then how can you remember? Here you can see du has s and v, so it should be s and v. H has s and p, because if you look at dh is essentially du plus pdv plus vdp. That means so here ds and dp is there, that's why s and p s equals to 0. Similarly, dv is equal to vdp minus SDT, which essentially means if dg at constant pressure and temperature, it should be less equals to 0. Okay. And other one is the Helmholtz. dA. What will be the dA? In case of G, it is D and P is equals to 0. Okay. So there are these 4 conditions are there. Let me summarize it. First one is du SV less equals to 0. For irreversibility, for spontaneous should be less than 0. If it is equal, that means that is a equilibrium process. Second one is SP, S and P less than 0. DG ET. Okay. These 4 the conditions for spontaneous process. Okay. Hope it is clear. If there is any doubt, you can ask me. Okay. So now going to the 4th question. Yes. The partial derivative del T del Vp is equals to, there are 4 options. Okay. So to solve this is better to remember the thermodynamic square. Last day I discussed. This is basically a trick to remember the Maxwell equation. Nothing more than that. Okay. So from thermodynamic square, we have to find that T, V and T. But if you look at here, there is no pattern like that. T is there. T, after T we can have G or then we can have S. But we need T, V and T. So this is not there in thermodynamic square. So how we can do that? Here we have to do a trick. Just now, if you think, you can write equals to 1 by this. I think it's easy. We know these things. Okay. So if it is, then VTP is there this way. This. So del V del TP will be equals to this, sharing this common edge. So it will be del S del P T, and this is a this will have a minus sign. So we can write del V del TP should be equals to minus of del S del P T. So del T del Vp will be, as I written, that is 1 by del V del Tp. So it is minus of 1 by del S del Pt. So it is minus del P del S. So it is actually the option C. So this is very tricky question. Basically, if you want to find these, then it is very difficult finding del T del Vp from Maxwell square, from thermodynamic square, or from Maxwell equation, because such thing does not there. But if you reverse it, del B del Tp is very common. So del B del Tp you can find out easily from Maxwell equation or from the thermodynamic square, and then by equating this, we can easily identify the form. Okay, next question. This is a numerical question. First, let me write it. 10 moles of a gas allowed to expand from a state A at 10 atm and 300 Kelvin temperature to state B, which was at 100 atm and 600 Kelvin. If the value of Cp is 6.995 calorie per degree centigrade, then asks to calculate the entropy change of the process. So here 10 moles gas is expanding from state A, which is at 10 atmosphere and 300 Kelvin, to state B, which is at 100 atm and 600 Kelvin. The Cp is given, and we have to identify the entropy change here. Okay. So clearly we have to use that formulas. We have three formulas. Among three formulas, we have to use one. So here temperature is changing, and also the pressure. So temperature and pressure is changing. So which form we have to use? There are three forms. Here pressure and volume, pressure and temperature. This form we have to use to identify the del S. So del S will be Cpln T2 by T1 plus, no, not plus, minus nRln P2 by P1. Okay, now just we have to put everything is known. Cp is given, so Cp is, first we can do 0.303 Cpln, instead of ln it will be now log T2 by T1 minus 0.303 nr log P2 by P1. This is del S. Okay, so now what is the Cp? Cp is this, but this is this Cp is for 1 mole. Okay, this is molar. Actually this is actually Cpm. Cpm is given for 1 mole. Then this Cp will be, can write it n Cpm. So if it is n Cpm, then it will be 2.303 into n is 10 mole, and it is 6.955 log P2 is 600, P1 is 300. Yes, this is T2, this is T1. Similarly, this is P1 and this is P2. You can write N is again 10. R we basically know is the universal gas constant. It's in 314. We have to use in calorie because this is given in terms of calorie. These things we have to keep in mind. We have to be consistent in terms of the unit. Okay, so if it is 8.314, then it is log 100 by 10. Okay, so if you do it, then it will be 303 into 10 into 6.955. It is actually 2. Yes, and it is okay. One thing, P2 is 100, P1 is 10. Yes, T2 is 60. Check. And formula is P2 x. It's okay. Yes, yes,
Given in calories. CP value is given in calories, and you are writing the R value in joules.
yes. This is in Joule.
So, but here the CP value is given in calories.
Yes, we have to change later.
So I think you can directly put the R value as either 2 calories or 1.98.
Yes, we can also do that. Okay.
Thank you. Thank
Otherwise, we can also change later, doing this part separately and this part separately, and then we can also do that. Okay. Okay. So now these things we have to do. This is again 2.30398, and this is log 10. So now we have to just calculate these things. Let me do the calculation. 2.303 into
you. It is only one. It is only 1.98, not 1.199. It's only 1.98.
okay, yes, sorry, 1.1. Okay, that is it. Thank you. Okay, so it is 10 into 6.955. So this arises as 48.2170, and this part is 2.303. Log 10 we know it is 1.98. So it is 45.5994. Okay, so the overall answer will be, we have to just subtract. Yes. So it is 2.6176. Okay, and what will be the unit? Unit is same of the CP. CP has the unit calorie per degree centigrade, so it will be the same unit, calorie degree centigrade inverse. So this is our del S, the entropy change. Okay. Also, they can give the option in terms of joule. Then we have to again convert it from calorie to joule. That we can do. Okay, for next question, question number 6. Okay, assuming that there is no chemical reaction Okay, till reaction. Then the change in entropy. Yes, change of entropy when 2 moles of N2 3 moles of H2 and 2 moles of HN3 are mixed. That means they are asking the entropy of mixing, but the constant temperature. Okay, this we have to find out. Okay. So now, okay, so what have 2 moles of N2, 3 moles of H2, and 2 moles of HN3. So what was the formula? We know that del S mixing minus NR. We can write in terms of ln. Okay, so minus NR ln xi ln xi. Okay, so sum is there. This one. Okay, this is the entropy of mix formula of entropy of mixing nrxi ln xi. So here I is basically 1, 2, 3. Three substances are there: nitrogen, hydrogen, and HCl. So what we can write? If it is in terms of log, then it will be 2.303. But now it's N2. Let's this is the n of N2 divided by n of N2, n of HN3 plus n of H2. So it will be 2 divided by 2, 3, and okay. It is a hydrogen gas has how many moles here? 3 moles of H2. Okay. So 3 divided by 7. And X it will be again 2/7. So the del S mix, that will be 2, 3 r n of H2, first n of N2, log of 2/7 plus what's going on, n of H2 3/7 log of 2/7. Now NP, this is 2 log 2/7 plus this is 3 log 3/7 plus this is again 2 log 2/7. Now here we will put it in joule 314. So it will be minus sign is there, so it is minus 2 into 0.54 log 2/7 minus 1.102 minus 2 into 0.54. Okay. So if you do this, then into this is plus 1.0802 again 1.08. So it is into 0.262. Yes, so it is joule per Kelvin inverse. So it is actually 63 joule per Kelvin inverse. Okay. So this is our sixth question. Think. Okay. So let me change this. Right. Think. One. Here. Wait. Okay, let me I think charge of my pen is Yes. It's probably not connecting. Screen CPU. Sorry for inconvenience. Can let me try it again. Yes, now it's visible. Okay, so it was question number 6. Now question number 7 would say that calculate Cp minus Cv for Van der Waals gases. Okay, so in last class or in class we have evaluate the Cp minus Cv is actually NR, but this is for ideal gas. Now we have to do it for the Van der Waals gas. Okay, so this is not trivial because the equation of Van der Waals gas is different. It's complicated compared to our real ideal gas. So for that, we know for Van der Waals gas the equation is E plus A by V square V minus B equals to RT. This is for 1 mole. Okay, and Cp minus Cv in last class we have already proved it is equals to, in general we can write it. Okay, so now we have to use it. So here we have to evaluate two things, del P del TV and del V del TP from this equation. Okay, so now let us start. First is P plus A by V square V minus B equals to RT RT by V minus B. So it's del P del TP as we have to differentiate these two terms in terms of temperature. Volume is constant, so it will be just R by, let me do it explicitly, del del T of R by V minus V at constant volume. But this term will be 0 because A is also constant, V is also constant. And this term will give R by V minus V. Okay, so this is our this term, but we have to now evaluate del V del T. For that, we have to do some numerical exercise. Let's for second part. This is again our action. So we can differentiate both sides with respect to temperature and it at constant pressure. If you do it, then we can write and this will be okay. Here both R and T. It will only give R. So now what we can do, so here it can be del V del T because it is at constant pressure. Okay, equals to R. And there is yes del V del T P F square, okay, plus V minus B into two terms are there, right? That's why we have to consider both of the terms here. I think I have written only one terms. Yes, another terms is there. V del del P A plus P plus A by P square. Now it's equals to. Okay. So there are two terms. First, we have taken out this. Then we have d by b is taking differentiating with respect to temperature, and next v minus b is coming out, and we are taking the derivative in terms of temperature of this term p plus a by p square. Okay, so here this arises, and the second term gives us it is also at constant pressure. So the first term, this t is constant, so it will not contribute. So only it will contribute the del del t of a by v square. So we can write v by b, and this t. A is constant, so we can write it as minus 2a v cube del v del t t. How? Let's say this is this derivation, right? So a is constant, so del del t 1 by v square. So we can write it as 1 by v square into del v del t. So it essentially gives that del v del t t. So that is written here 2a by v cube and del b del dp. So this is written there. Okay. So I'm erasing this. This is trivial. So equals to r. Yes, equals to r. What we can write now, p plus a by v square. P plus a by v square is rt by vb, v minus b. So it can be written as rt by v minus b into del v del dp minus 2a by v cube b minus b into del v del dp. That is equals to r. Okay. So del v del dp is essentially be the r divided by the whole thing, because both del v del dp is common, so we can take common, so it will be rt divided by v minus b minus 2a v cube into p. Okay, so this is del v del dp, del v del dp both. Now we have both the terms, just we have to identify that cp minus cp. So cp minus cp is p into, first is del p del p v, the second one is del p del dp. So del p del dp is r by v minus b, so r by v minus b into this is r by this whole term. So this is r p by v minus b minus 2a into v minus b divided by b cube. So it can be written as rt by b minus b into r by, now we can take common rt by b minus b. From here it will be 1 minus 2a b minus b squared divided by b cube rt. So this will cancel. So we'll have this. So this is the general form. Now we can do some approximation to make it more streamlined. Just now we know that V is greater than B for van der Waals gases. If you imply that, then V minus B whole square can be treated as V square. So if you put it here, then it will be R by 1 minus 2A V square divided by V cube RT. So it is essentially VRT. Okay, so you can write, so Cp minus Cv is R into 1 minus 2A by RT to the power minus 1. Okay, so it is actually very close to 1 plus V by RT, because 1 minus x to the power minus 1 is can be written as this when x is less than 1, then it is, we can write this. Okay, so approximately this is the form, or we can also use that our equation when we can write it cp minus cv r into, okay, so this is the cp minus cv for generally this is used this form. This is the form cp minus cv is r into 1 plus v by cv. Okay, so this is not very straightforward because we have to evaluate this part. This is not very trivial to evaluate. This is rigorous to do. Okay, now the which question it is? Question number 8. Question number 8. Okay, this is very important again. Derive the third law of thermodynamics. Means a mathematical form of third law of thermodynamics. You have to rewrite that. So what is the statement of the third law of thermodynamics? That we have to understand first, then we can implement that to derive the third law of thermodynamics. For that, we have to use a relation that we have already derived. Using that relation, we can eventually derive the third law of thermodynamics, the mathematical form. The entropy of an pure and perfectly crystalline solid is zero at absolute zero. Means a 0 Kelvin. So at 0 Kelvin, the entropy of a pure and perfectly crystalline solid is 0. So how we can implement this? We know that the ds is cvdt by t plus nr dv by v. This form we have already derived here. This is ds equal to cv dt by t and p is dv by t, and p we can think like that. If you use the ideal gas equation, then that is the form. But here we can't use that because we are considering the perfectly crystalline solid. So for that we have to write it. Okay. So for that we have to write like this. Okay. Now if you integrate, then there will be integration sign. So delta S this thing. But for solid, we know that dV is 0. Solid or liquid cases, we don't consider that volume is changing. That means this term will be 0. Okay. So if that is, then we can directly write for solid is Cv dt by T, del S. This is called del SP. Okay. For perfectly crystalline solid, this is the case. So now, if you make this is, let's say, the integration, this integration, if you done this integration from 0 to p, then it will be s0 to st. So it essentially means that st minus S0 is, okay, no, actually it is Cp. Okay, 1 minute, one mistake is there. Okay, sorry, this form is correct, no problem is there, but another form we know we have to use that Cp dt by T, this form, this form. But this is again for, we can say like this is for gas. So no, this form will not also be correct. It was correct. It was correct previous, because that form is true for the gas, but we have to discuss for solid. Yes, it's correct. We are doing the correct thing. So Cv dt by T, and this is varying from 0 to S0 is basically 0. This is the statement that entropy of pure and perfectly crystalline solid is 0. So this is 0. Then we can write that St temperature, entropy at any temperature can be evaluated following this relation. Okay, it was right earlier. So Cv dt by T, we can evaluate dt using this, but Cv is not here independent of temperature. If it is independent of temperature, then we can bring out from the integration and we can easily do like this. This is T. Like this. So we can do like this. Okay. But for solid, basically, Cv is not independent of temperature. Okay, next is, yes, 9, question number 9. Proof del U by T square is, this we have to prove. Similar kind of equation, relation already proved in class using the enthalpy, and the Gibbs free energy. This is using the internal energy and the Helmholtz free energy. So what was that equation? That equation was del H by T square, that is equals to minus, this is called Gibbs Helmholtz relation. This is okay. So if you want to prove this two relation, first relation is already proved. So let me do. We know G equals to H. This is not important. A equals to U minus TS. This is, we have to prove this. This is already proved in class. So A equals to U minus TS. So what we can write that STT. And from first law of thermodynamics, we know du equals to TdS minus PdV. If you put it here, then we can write it minus PdV minus STT. So del A del B V is actually minus S. Okay. So if it is the case, then what we can write from here, from this equation, it can be written as del A is equals to del U plus T. Just okay. Let me see. If it is, then we can write that del A is equals to minus Now del A will be del U plus T delta S from here. So if you put it, this delta S, it will be T into delta T at constant volume. Okay. So you can write it that del U equals to minus y T squared will be there from this equation. Delta U by T squared will be 1 by T, and delta A will be there into 1 by delta A T. This, so this is nothing but X. So this is called Helmholtz relation, and this one is Gibbs. So these two relations are called Gibbs-Helmholtz relation. Okay. So probably the last question of the day, residual entropy. What does it mean? This is also very important. Uh, there are some solids basically. We studied here that this is the third law of thermodynamics. For perfectly and pure crystalline solid, this is true. Thus S0 is 0, but all solids are not the perfectly crystalline and pure solids. So there are some solids which do not fulfill the perfectly crystalline form. So therefore some entropy is there even at 0 Kelvin. So for non-perfect or non-crystalline solids, there are some non-zero amount of entropy resides even at 0 Kelvin. That entropy is called residual entropy. Okay. Example of those solids are the solids like carbon monoxide, ice, solid H2, B2, and so on. So this residual entropy is written as S. S is also written S. The form is just Kb ln omega, form of residual entropy, where this Kb is, we know, Boltzmann constant, and this omega is important. We'll in class, the next few lectures, this will be covered. The omega is number of microstate. From here, the statistical mechanics will start. We'll see later, but this is the residual entropy, which is related to our third law of thermodynamics. So this is number of microstate. Okay. So now we'll go to the next question. What will be the question? If there is any question left, let me check. Then should do.
Hello.
Yes. Huh? Yes.
May I know how shall I pronounce your name? Is it Shuvadip or Shuvadip?
First one
How
is
do I
correct.
how do I call you?
First one is correct.
Shuvadip.
Yes.
Okay, Shuvadip. I just want to speak to you for only 1 minute. Okay,
Okay.
sir. Your main focus is on the derivations of the different equations. But
Mm.
it would be better if you focus on solving the numericals. That will be very helpful. Instead of deriving some equations, I think the derivations will be directly available from the textbooks. But if your
Mm.
focus is on the solving the different types of numericals and exposure, more exposure should be given on the numericals. It will be better, I think.
Yes, but for that, I was waiting for the deadline of the assignment. Then from
No, no.
assignment also and
Assignment.
other questions also we can do. But before that, the similar kind of question I can't discuss. Then it will be similar straightforward to that assignment. That's why today I thought that, but deadline is increased because previously to 2nd February.
No.
But
Let me tell you one thing, Shuvadip. See, previously I did one course, on not on this, but a different course. But when a particular assignment is given, again it is a numericals. But while dealing with
mm,
the numericals, the assignment, the people like you who are dealing with the problem solving sessions,
mm,
they use it to discuss only the problems. And like nearly for 2 hours. So out of 2 hours of the problem solving sessions, at least two or three bits from the assignment. They are not real examples from the assignment only. Different types of models and similar models with different digits were explained, so that
but
so that a student can answer those assignment questions easily. So that should, I think, that will be that will help the students in getting score in the assignments also.
okay, but as this is kind of theoretical
No, no, I'm not
course,
saying.
that's
I'm
why
not saying this is okay. This is very good. Theoretical, this is good. I'm not denying it. This is good.
mm,
But problem solve, if the focus is more on different types of problem solving sessions, then it will be better to the students, I think.
okay, okay.
This is only small suggestion.
Okay, I also thought that, but I was waiting for the deadline so that I can do from there also and similar kind of question. I did not include that kind of question because it will be then resemblance with the assignments and probably it will kind of similar. That's why I did not include to the
No,
schedule.
the students should have a more help on this all different types of solving the problems. That's it.
Okay.
Okay, no problem. It is up to you to decide. And then may I know which platform you are using in writing? Your handwriting is very good. I appreciate your beautiful handwriting. That is very excellently you are writing on the board. May I know which platform you are using?
This is just I'm using my tab and the notes. In notes, I'm just writing.
No, no. On which platform you are using? That is a tab is okay. Are you using Microsoft Whiteboard or
No, no, no.
which
This is
word which whiteboard you are using?
no. This is Samsung notes available in Samsung tabs. That
Samsung tab you are using. Okay, okay.
mm,
Samsung pen tab. Is it a pen tab?
yes, pen tab.
Samsung pen tab.
Mm.
Okay, sir. Please proceed.
Okay. Let me discuss another question. Is the entropy of mixing 10 moles of helium and 10 moles of oxygen at constant temperature and pressure, assuming both to be ideal gas. Okay. So again, it is question of entropy of mixing. There are two important things are there that del S mix that is discussed already, and another one is del G mix. So from these two, there are so many questions are asked. So in next part we'll discuss del S mix, but here del G mix. So here again del S mix we have to calculate. The similar way we have to do. The form is minus R sum over I Ni ln xi. This form we can use, or we can use nr sum over I xi ln xi. Both are the both same. Here n is total mole, and this is the moles of ith component. Okay, so among two we can use any form. So let me deal with this. So del S mix will be, if you convert it into log, then it will be sum over I ni log xi. So here are only two components are there, two gases. One is oxygen, another one is helium. So we can write it x1. Now x1. What is the x1?
This is still new, it is still new. Ln half plus ln half plus
10 moles
ln
of
half
helium.
into minus 2 ln 2.
Yes, is there any question? Okay. So x1 is n1 divided by n1 plus n2. Both are 10 moles, so it's straightforward that it will be half. Similarly, x2 will be also half. So if you put it here, then del x mixing will be n1. N1 is 10 log x1 is half plus again 10 log half. So we can write minus 2.303, and R is here 8.314 in joule. So it is 10 will be there, and it will be okay. We directly 2 to log 0.5 or half. This we can write. So it is minus 2.303, 8.314 into 20, and this is 0.3010. If you multiply it, then you get 1153 joule per Kelvin inverse. Joule is coming, the unit is unit of R and Ni. This will define the unit because Xi don't have any unit. So it is joule per Kelvin inverse. It is taken in term in joule, that's why it's coming in joule. This is the question. So now if you have a different question, as you are one thing, you can let me check whether there was. Okay, yes. Question number 12. The change in entropy when 1 mole of an ideal gas is compressed to 1/4 of its initial volume and simultaneously heated to twice its initial temperature. So entropy change we have to calculate when 1 mole of ideal gas is compressed to 1/4 its initial volume and heated twice. So what is doing? V is changing. V is changing to V by 4, 1/4. So let's say V1 is changing to V2 and V2 is actually V1 by 4. And also temperature is changing T1 to T2 and heated to twice its initial temperature. So T2 is eventually 2T1. So volume and temperature is changing. So we have to use among three equations, we have to use a proper equation where volume and temperature both are changing here. Volume, this equation, volume and temperature both are changing. So it is, so del S will be CVln T2 by T1 minus NRln minus, let me check once, plus NRln V2 by V1 plus NRln V2 by V1. Okay, so T2 by T1 is 2. So it is CVln 2 and NRln, what is V2 by V1? V2 by V1 is 1 by 4. So it is 1 by 4. So you can write it CVln2 minus NRln 4. Okay. So it will be, you can write it like this. So it will be CVln2 minus 2NRln2. Okay. So CV minus 2NRln2. So this will be the entropy change as the other data is not given. So this form is the final form. If the CV or N is given, then from there we can, here CV is actually N into CVM. Okay, so we can again simplify this as del S CVM minus 2R into N ln2. CVM is molar heat capacity for 1 mole and it is total. So again we can write it del S bar is actually CVM minus 2R ln2. This is for 1 mole also. So okay, so this is also correct. So probably for is the question left. Let me check. For today's class, it is covered. Okay, probably it's done. So if you have any question, you can ask. Otherwise, for today, I think there is no question left.
Shubhadeep, the pen tab is okay, but are you writing on the whiteboard sharing of Google Meet?
Whiteboard in Google Meet, I don't understand.
No, see, you are writing on the pen tab, that's okay, but
Hmm.
some platform of whiteboard should be shared, no? I wanted to know which whiteboard is shared. Is it from the Zoom or from the Google Meet or which one?
Google Meet.
Google Meet whiteboard is shared in this.
No, no. You have joined in Google Meet. We have joined in Google Meet, and I am sharing the screen. So that's why you can visible my screen. That screen is from my
Oh,
tab screen. That's why you are seeing that tab screen, which is
okay, okay. I thought you are using a Microsoft whiteboard. Okay, no
no.
problem.
In that case, we can't. I can't use the pen. Pen will be
Uh-huh.
needed.
Okay, right. Okay,
Okay.
done. Thank you very much.
Okay. So okay, I will keep in mind your suggestion, and I will try to give more numerical exercise.
Thank you. Good luck. Once again, I appreciate your
Thank you, sir.
handwriting. A neat handwriting.
Okay. Thank you. Is there any question? Other question?
Thank you, sir.
Okay.
Can you please go back to the change in entropy which you have discussed initially? First problem, very first problem.
This one.
Not that numerical and change
Okay.
of entropy.
This one.
I think you have. Can you please verify the calculation part in that?
This problem?
Yes, very first one. Yes. CPM. Yes.
No, I think calculation is correct. I am trying.
Calculation, but I think delta S we are getting a negative value. Can you please verify
No,
this?
no, not negative. It's positive. Delta S
10
is
into
delta
10,
S.
10.
This
It
is
is
positive.
it is not it is not mixing. It is only change in entropy.
This is
Yes,
entropy
yes.
change.
That's it. Can you come down, please?
Mm.
Can you please come down? That's it. 2.303 into 10 into 1.98. See, this is 19.8, sir. 10 into 1.98 is 19.8. We can take out the 2.303 common. So that
Mm.
10 into 6.9, 10 into 6.955 minus
Let me to calculate.
okay 69.55. Okay. I'll check it out, sir. No problem. You please proceed, sir. No problem.
Okay, let me check
I'll
again
I'll check
also.
my answer. I'll check my answer,
Yes,
sir. No
yes.
problem. Please proceed.
Okay. I think probably
Thank you.
it's correct. I also did in the calculator.
Okay.
And
Okay. No problem. I'll check it out. Please proceed.
okay,
Please proceed.
okay. So for today, I think there is no question left. If there, I will check the numerical question again. If there is any mistake there, then I will also verify in next class.
Thank you. Thank you. Good luck. Done.
Okay. Okay. So we can stop here today. Okay. Okay. So thank you for joining. We'll meet again in next class next week. You can leave now.